A recycling factory pattern in Delphi. The problems of using and reusing many varying size objects in an application can cause fragmentation of the heap that can slow down processing speed. This article uses a factory object to make and recycle objects with minimal fragmentation effects. One of the patterns in the classic book Design Patterns, Elements of Reusable Object-Oriented Software is the factory method, where objects are created, and I recently had to use it. The reason? A memory fragmentation problem in a simulation system using a large number of objects to hold numeric arrays. There were several numeric array types, in fixed sizes varying from 1500 x 1 to 5000 x 10 numbers, either integers or doubles. These were used in a simulation of a financial calculation over a 2-year period, creating data on each of 472 simulated days from historical data. On each day, data was read in from a database, processed, then saved out. Despite extensive leak checking, the software would only run for a number of simulated days before eating up the Windows swap file. Memory leaks were carefully tracked down and eliminated, but my hair was still in jeopardy. The app would not run for longer than about 30 simulated days before it had committed over half of the anti-paging file, this on a 512 MB RAM system. Close investigation showed that on each day it ran, the allocated memory grew from 5 M to about 80 MB, then shrank back to about 5 M again. On the face of it, not a problem with 512 MB to play with, but watching the WinNT Manager showed an increasing amount of memory committed. Fragmentation. The problem was simple, it was heap fragmentation to blame. This occurs when many different objects are created and then destroyed repeatedly. As each object is created, it consumes memory from the heap. If objects were created and then destroyed in reverse order, it probably wouldn't happen, as all the freed memory could be merged into one large block. But in any system with a large number of objects, the order of creation and destruction will never be symmetrical. My app can easily have up to 50,000 objects in memory at the same time. So when an object is destroyed, a pointer to the freed memory block is added to a free block list. When other requests for memory are made, Windows tries to allocate those requests out of the freed list first. Fragmentation happens where a large block like 1 MB has been requested and subsequently freed up, followed by a request for a smaller block. This is taken from the first block on the free list that may well be the 1 MB, which leaves only 900 KB free. Then another request for a large 1 MB block comes along. It cannot be satisfied from the free list and so it is taken from the heap. If the creation/destruction cycle happens enough times, the large blocks on the heap are chopped into smaller bits. The physical RAM is exhausted and replaced with virtual RAM. Windows Heap Memory Management, and Delphi, is quite clever. It takes a lot to get it to fragment. But under the relentless pressure of a large number of objects being created and destroyed, the memory manager will gradually cave in. When Windows runs out of free RAM, it starts swapping pages of RAM to disk and performance takes a nosedive. Your app could be galloping happily along at 100% CPU until swapping starts. It then becomes a funeral march crawling along at maybe 7 to 10% of CPU, taking forever to run. Disaster. Microsoft have put a lot of effort making the memory manager as efficient as possible. For example, under NT, there is a two-stage process of reserving and committing memory. If your app requires 100 MB, it is reserved when the app is loaded. But only when the memory is accessed are the reserved pages committed. If you want to learn more than you will ever possibly need to know about this and other topics, I recommend the book Inside NT, published by Microsoft Press, but get the David Solomon version, which is the later edition, not the Helen Custer first edition. Factory patterns. So I needed a non-fragmenting way of creating many objects, using them, throwing them away and then doing it all again without Windows running out of virtual memory. Having recently read the pattern book, I thought, why not use a factory, i.e. a factory object that creates objects of a specified class. I then went one better and made it environmentally friendly, so it gets to recycle all its manufactured objects instead of destroying them and without the associated fragmenting problems. The icing on the cake was to make the factory able to expand its capacity without loss of access speed. Rather than have one factory class for all class types, I took the simpler approach of passing the object class into the factory as a factory creation parameter. When the factory is created, you specify both the class of objects it can make and the initial storage capacity of the factory. This size can be changed upwards by calling the grow factory method. I suggest you only call this in exceptional circumstances. The link back to the factory from each object is needed, so all factory-made objects, FMOs, must descend from a T-factory object class instead of TObject. This adds a factory reference which is stamped on all FMOs so that the object knows which factory to use to recycle itself. Instead of creating an object, your app requests one from the suitable factory by calling its requestObj method, which returns a class object back, and you convert it to the right class using as. Finally, when you have finished using the object, you just call its recycleSelf method. No creation or destruction except of the factories themselves. How it works: when the factory is created, all of the objects are physically created in one contiguous block of RAM. A T-list, block list, object holds the address of each of these blocks. Each time you grow the factory, a new block is created and added to this list. The method addObjects creates the specified number of objects using the RAM from the block. If you write code like this, be aware that just doing a tObject, address, is not enough to create the object. You must always call object class.initInstance, address, to transform it into a proper object. InitInstance clears everything to 0, nil, etc., but more importantly, it sets up the VMT. The factory also contains another T-list, free-list, which holds the address of every unused object. All of the donkey work of filling the factory is done in the private method addObjects. For each object created in the block, this converts the pointer ptr into an object, using factory object as the class of object created. This must always be a descendant of t factory object. Obj holds the object reference and links the factory to the manufactured object. Ptr is then incremented to point to the next object in the block by adding fsize. To get an object, your code calls request_obj, which pops the reference off the end of the free list and returns it as the first requested object. Recycling is the reverse. It pushes the recycled object reference onto the end of free list. One thing to bear in mind: when a factory-made object is in use, the factory does not have any reference to it, although the memory occupied by the object is contained within the factory. Replacing create and destroy using the factory requires you to use manufactured objects slightly differently from normal. You no longer create or free them explicitly, instead you just request the relevant factory for the object. Unless the factory is empty, this will always work. You have to modify the initialization code in the constructor and termination code in the destructor routines. There are two approaches. 1. If the object has a simple create constructor with no parameters, you can rename it to procedure init, override and remove any inherited create calls. The factory always calls an init method when any object is requested. By default this does nothing, but you can override this so your init will be called automatically on every object requested from the factory. 2. If your original create has parameters, rename it to something like initialize and remove inherited etc. calls. After the object is requested, call the initialize routine, e.g. myRoutine.initialize. If the object has destructor code, rename it to procedure done, override so that it's called automatically when the object is recycled. Init and done are similar to create/destroy but without the baggage of the construction or destruction mechanism. As a slight digression, I understand that there are arguments in the Delphi world in favor on one part creation or two part. One part is where the constructor has parameters and completely sets up the object. In the two-part approach, the constructor just creates a blank object which is then initialized by a later method. The factory approach, I think, is firmly in the two-part camp. When the factory is destroyed, all the allocated memory blocks are freed up. Before this, the factory checks that the number of objects in the free list matches the capacity. If you have forgotten to recycle all your remaining objects, it will raise an exception. Comparison program. This shows the benefits of factories. At work my app had many different sizes of objects in differing quantities, but a 15,000-line program would not exactly be publishable. After a bit of trial and error I came up with a short program that can show fragmentation. However, this depends on the size of the different objects, how many there are, available RAM and for how long it is run. Also, fragmentation seems to occur more quickly on NT 4.0 than 98, which suggests that maybe 98 has a better memory manager. When run, it creates and destroys a large number of objects repeatedly for the specified number of days. It also does exactly the same thing using a factory. Each day is timed and both sets of times plotted using chart. I used 3 types of objects, all descended from tTestObj, which descends from tFactoryObject. Small objects are 2K in size, medium are 40K and large are 800K, but these sizes are defined by constants and can easily change. The demo program allocates 100 MB for the normal objects and another 100 MB for the factory. Both contain the same number of objects divided equally by size between the 3 object types, so there are 17,406 small objects, 873 medium, and 43 large. In the object creation procedure Timonata, these are randomly created and added to the list. At the end of the day they are freed up and the process repeated next day. The same is done using 3 factories with all manufactured objects added to a factory data list. On AP2400 with 256 MB running for 100 days, there was a modest increase in the time for both the factory and the normal object creation. Commenting out the normal creation confirmed this suspicion. The increase was much less over a 1000-day run using factories against 100 days with both normal and factory testing. I guess that this was caused by increased page swapping due to fragmentation affecting both processes. Some other combinations of sizes and number of objects under Windows 98 showed no fragmentation. I implemented this originally using a T-list for both test data and factory data and changed it later when I realized that repeatedly adding and freeing up 18,000 pointers was also adding to heap fragmentation. I'm not advocating ditching string lists completely in your code. They are very useful, as are T-lists, but if you have to manipulate a large number of items, it might be better to use your own list structures. If you want to use T-list or string list for this purpose, it's probably better to completely fill the structure with nil pointers, so that count equals capacity, and use an integer to hold the index of the last pointer. This app also confirmed that the factory code is very quick at allocation and deletion, typically 30 milliseconds for 18,000 objects instead of the 870 milliseconds that normal creation/deletion took. Tigi's article originally appeared in Delphi Developer Magazine. Sources.zip